Share screen. Share. Let's see if this works. Plugin is required. Yes. Okay, go ahead. All right. Let's get this. I've now moved into the 20th century and got myself an iPhone. So I'm learning how to use it. Mostly I don't know how to use it. Yeah, okay, so there's a lot to review. My approach to the energy dependent Green's functions has been to try to create a physical model of it that can help you visualize what the wave functions look like. Because you can write down formulas all day, but it helps to have an image of what they look like. So the image I'm trying to create is that of what you call an energy dependent Green's function for water waves. And to do that, you imagine that you've got a lake that's been quiet since the beginning of time, and you go up to it, and at time t equals 0, and at location x0, as you see right here in this delta function, you begin poking your finger into the lake with a frequency omega. In the quantum problem, the frequency is identified with E over h bars is the frequency. And so this generates waves, and the point here is to visualize what those waves look like. So they radiate out from your finger. They interfere with each other if they bounce off shores and stuff like that. And after a while, the transients die out because of damping, and you end up with a wave pattern which is evolving at the frequency at the driving frequency. So this is what happens when you drive a harmonic oscillator at a driving frequency. Because of dissipation, after the transients die out, the response is at the same frequency as the driving frequency. And so what you do is you then strip off that time dependence. It's basically just a wave that's moving at a given frequency. You just get the spatial part of the wave, and that's the energy dependent Green's function, or the frequency dependent Green's function. That's what it is. So you can just picture this as waves. It's waves radiating outward. Now, the damping is what causes the transients to die away. And depending on the damping parameter, it'll take more or less time, but the damping is exponential. So nominally what we do is we say we let t go to infinity, but really you just need to let it go long enough that the damping is essentially gone. However, it's worth noting that the amount of time you have to wait depends on the damping. And as the damping goes to 0, the amount of time you have to wait gets longer and longer. All right, anyway, so we apply this idea to the Schrodinger equation, and we take this source function and use it in the time-dependent Schrodinger equation as a driving term, using the outgoing Green's function to find out the solution. And if you do, what you should get is should get some psi that's got the time dependence of the driving term. You see the driving term here is represented by an energy E, which is a parameter that you get to specify. You can make it anything you want. It's equivalent in the lake analogy to the frequency of the driving term. And then the wave field that's left over is the Green's function. It's parameterized by the initial position, parameterized by the frequency of the driving term, and otherwise it depends on x. So it's a wave field that depends on x. And I say as t goes to infinity means long enough to let the damping go away. Now, if you actually do this for a Schrodinger equation, what you get for this Green's function, you get something, you can indeed split off this time-dependent factor. What's left is an integral, which it turns out is actually not defined. It's not defined because the upper limit, t goes to infinity, the thing just oscillates and never approaches a limit. And the reason for that is that the Schrodinger equation doesn't have any damping in it. Lakes do, but Schrodinger equation doesn't. And so what we do is we introduce an artificial damping into the Schrodinger equation, which, as it turns out, is equivalent to taking the energy parameter of the Green's function, which is also the energy-like parameter that appears in this formula here. This formula, you see, is basically a one-sided Fourier transform of the propagator that we talked about last semester, the matrix element of the time evolution operator. It's one-sided because the time integral only goes from 0 to infinity, and it does that because the time dependence is turned on at t equals 0, you see. Is there a question? I thought I heard the question. Okay, in any case, this is the formula you get, but as I say, is not defined because of the upper limit. It just oscillates. So to introduce damping in the Schrodinger equation, it turns out it's equivalent to replacing the energy E by E plus I epsilon, giving it an imaginary part. Epsilon here makes you think that it's small, and we will let epsilon go to zero at a certain point, but actually epsilon doesn't have to be small. It's just a damping parameter. So we'll call this complexified energy Z. And if I plug that into this formula that we got here, both there and there, then I get a nominal Green's function, which is parameterized by this complexified energy. Here's the complex energy plane, the real energy, imaginary energy, and there's this complex energy with the positive imaginary part. So this leads us to define the Green's operator. This is an operator version of the Green's function equation up above, which is basically the one-sided Fourier transform of the time evolution operator, but with a complexified energy, which has a positive imaginary part. And if we do this, the integral is now defined. The upper limit causes no problems. And we can do the integral, and we find that the Green's operator is 1 over z minus h. This is the Hamiltonian operator, so I put a hat on it like that. Okay, so that's part of what we did last time. Now, if you follow the logic of what I'm doing, I'm claiming that this water wave analogy gives us the Green's operator, and then we're applying those ideas to the Schrodinger equation just to see what formulas we get. I haven't proven that anything really is a Green's operator or function yet. I'm just following this idea. We'll do that a little later. But in any case, this then leads to g hat of z, the operator Green's operator, is 1 over z minus h. This is sometimes called the resolvent operator, by the way. And we find that this is defined as long as the imaginary part of z is not equal to 0. It may also be defined when imaginary part of z is equal to 0. That's what we want. We want to let epsilon go to 0 now because that's the damping parameter. In effect, we want to introduce damping to get rid of the transients. And then having done that, we let the damping parameter go to 0, because all we're really interested in is the asymptotic wave field after the transients are gone. And that should give us the Green's function for real values of energy. That's the idea anyway. So then this Green's operator for complexified energy Z, just using the fact that it's a function of a Hamiltonian, using our formula for functions of an operator, this is assuming that the Hamiltonian H hat has a discrete set of bound eigenvalues at negative energy, maybe with degeneracies indicated by alpha, and a continuum, as you can see here in this energy diagram. Here is complex energy diagram. Here's the discrete bound states, and here's the continuum of positive energy states. Let's just assume that the Hamiltonian has a spectrum like that. Then there's two contributions to the formula for G, and they have this denominator e plus I epsilon minus En for the bound states minus E prime, which is the variable integral, energy integral you're integrating over to run over the positive real axis like this for the continuum states. Okay. Now, the question then is this thing, if we let the imaginary part go to 0 to get a Green's function for real values of the energy, the first question is it even defined? Does it even work? And the answer depends on the cases. We take 3 cases. In what I call case A, we imagine an energy whose real part lies between, first place, it's negative, and it's not equal to any of the discrete eigenvalues. So it lies between discrete eigenvalues, as you see here. And if you let epsilon go to 0, it approaches the real axis coming down like that. Now, if you do that, if you look at this formula up here, if E is not equal to any E sub n, then this denominator is never equal to, this E minus En is never equal to 0. And so just taking the limit where I epsilon goes to 0 is going to be the same as just replacing I epsilon by 0, just evaluating at epsilon equals to 0, because there's nothing funny that happens with the denominator. Likewise, in the positive energy term, the E prime is a variable of integration, which is always positive. The E here is, the E here is the epsilon, the E here is the energy-like parameter of the problem, which is negative. So E minus E prime is never equal to 0. And again, you can just set epsilon equals to 0. And if you do, this is what you get for G of Z when you have, in case A, negative energy not equal to any energy eigenvalue. Now in case B, we're still negative energy, but the energy E is equal to one of the energy eigenvalues. Let's call this one E sub n right here. So E is equal to some E sub n. And if you do that, then you can see that this denominator, E minus En, is going to go to 0, so the Green's function diverges. However, if you take epsilon small but non-zero, what you find, going back to this formula here, if I set E equals to E sub n, then the E minus En cancels, and you just have the 1 over I epsilon for that one term, for that one value of n. So if epsilon gets to be small, that one value of n dominates, and what's left over, it's right down here, what's left over, as you can see, is the projection operator onto the eigenspace for that discrete eigenvalue. So although it diverges, before it gets there, it's proportional to this projection operator. All right. Now then, if E is positive, then what happens is, well, all the negative denominators are well defined, but now in the positive, since both E prime and E are both positive, it means in this variable of integration, you're going to run right over the place where the E is equal to E prime and the denominator just turns into I epsilon. Letting epsilon goes to zero looks like you're going to get a zero denominator under the integrand. Well, it turns out that in spite of that, this integral is defined. I'm not going to prove that, but I'll give you an example of it in a few minutes where we'll see the answer comes out. In any case, to summarize all of this is that in cases A and C, the limit as epsilon goes to zero. This G of Z is defined for all complex numbers in the upper half of the complex plane when the imaginary part of Z is not equal to zero. But when we let the imaginary part approach zero from above, then we find that in cases A and C, the limit is defined. But in case B, when we're on a discrete energy eigenvalue, it's not defined. So to summarize this, taking the limit epsilon goes to zero, we have a well-defined Green's operator as long as the energy parameter is not equal to one of the discrete eigenvalues. Okay, I think that's mostly up to where we left off last time. Are there any questions about that? This is kind of convoluted logic, I know, starting with a lake and then introducing the epsilon parameter, but I think this is the way to understand it. It's really effectively introducing artificial damping. Any questions about this before we go on? All right, well, if not, then perhaps you appreciate at this point that I actually haven't proved that we have a Green's operator for the energy-dependent Schrodinger equation. The Green's operator for the energy dimension, well, first of all, a Green's function, what would it look like? It would be E minus H, the Hamiltonian, acting on the Green's function, G, which depends on x prime and energy E, would be equal to a Dirac delta function in x and x prime. This is in a 1D notation here, but that's any G that satisfies this equation is a Green's op. Oops, sorry. You need to complain when I'm messing up like that. Here's the wave operator. The Hamiltonian acts on the field dependence of the G like that. The x prime is like the initial position, and any function G that satisfies this equation is a Green's function for the time independent Schrodinger equation. It can be used to solve the homogeneous equations. If we put this in operator language, we'd have E minus H hat acting on G hat, which is parameterized by energy E, should be equal to the operator 1. And we go from the lower equation to the upper one by sandwiching it on both sides with x and x prime that gets like this. And if you do that, then the second equation is converted into the first. Second equation, however, is more general. It doesn't even require that we be talking about a system where x is even meaningful. It could be a spin system, for example. In any case, this is an operator version for the definition of the Green's operator. Now our Green's operator, let's plug in our Green's operator and see if it works. So E minus H, we want to apply this to the limit as epsilon goes to zero of 1 over E plus I epsilon minus H hat. And I'll write this way, bringing E minus H in as limit epsilon goes to zero of E minus H hat. And then I'll subtract I epsilon, I'll add I epsilon, and then I'll subtract I epsilon like this, divided by E plus I epsilon minus H hat. These are really operators, and if you want to talk about multiplying one times the inverse of the other, there's a question about the ordering. But since both operators are a function of the Hamiltonian, they commute with each other, and the ordering doesn't matter. So this is how I've written it here. All right, so you've got E plus I epsilon minus H above and below. So the first term just gives us 1. This is the limit as epsilon goes to 0 of simply 1 for the first term, and then minus I epsilon divided by E plus I epsilon minus H hat. Now, without the first term is easy, just the limit is 1. As far as the second term is concerned, the denominator by itself, that's all there was. That would approach G of E. That's our definition of G, which is defined as long as the energy parameter is not one of the discrete eigenvalues, as we just saw. So let's suppose it's not one of the discrete eigenvalues. Let's suppose we're talking about a place where the G hat of E is defined. Then that's what the denominator would give, which is a well-defined operator. But it's multiplied by I epsilon, and epsilon is going to 0, so that's just going to punch out the second term. This is just going to go to 0. So the result is this is equal to 1. And so what we see is that this strategy that we've got here of introducing damping and then letting the damping parameter approach 0 actually does give us a Green's operator. So it's useful for solving inhomogeneous Schrodinger equations. All right, gives us a Green's operator. Green's operators are never unique. There's always many solutions to them, but it gives us at least one Green's operator. Okay, now this Green's operator, if I write it out in terms of the integral that we evaluated, it can be written this way as 1 over IH bar. This is really just a rewriting of one of those equations I had in the earlier page. It's as I said, it's a one-sided Fourier transform. No. Let's do it this way. Let's make it g hat of z, where z is a complexified energy. So z here is equal to e plus I epsilon. So in particular, it's got a real, its imaginary part of z is positive. So g hat of z then is 1 over IH bar, the integral from 0 to infinity of dt e to the IZT over h bar times u hat of t. That was the formula we used to derive it a minute ago. And this integral can be done, and it turns into 1 over z minus h hat. So that's just a recapitulation of what we did on a previous page. Now, what I want to point out here is that if I'll remind you that we had the outgoing time-dependent Green's function for the time-dependent Schrodinger equation we call k plus and minus. K plus of t is the same thing as the Heaviside step function theta of t times u hat of t, like so. It just punches it out for negative times. And so using that, then I can write g hat of z is equal to 1 over IH bar. And now I can just put in an unlimited Fourier transform from all times dt like this, of e to the IZT over h bar times k plus hat of t. And so what we see is that the g that we've created is really just the Fourier transform in time, in which z is an energy-like, a conjugate variable that's conjugate to time, energy-like variable conjugate to time, of the outgoing propagator. That's what it is. So let's put a plus on this g that it's the same g I've got up above, but let's put a plus on it now to indicate its relationship to k plus. And as I said, this is the same thing as 1 over z minus h, as long as the imaginary part of z is positive. All right, now, this suggests that we define something else we call g minus of z, which is the same formula, except instead of k plus here, we put k minus using the incoming Green's function. We'll integrate over all times as above, e to the IZT over h bar, and we have k minus hat of t, like so. As far as k minus is concerned, I'll remind you that the k minus of t is equal with an overall minus sign of theta of minus t multiplied times u hat of t. You see that? K minus vanishes for positive times, and the step function, that's a minus t there, in case you can't see that right there is a minus t. So the theta function here punches it out for positive times, and it makes it non-zero for negative times. In any case, if we use k minus, then the obvious formula is this. So it turns out that if we analyze this g minus in the same way that we analyze the g plus, what do we find? Well, here's what we find. We find that this integral is actually convergent as long as the imaginary part of z is negative. For imaginary part positive, this is meaningless. Also, for real values of z, the integral is not meaningful. But for the imaginary part negative, it is. And what does it give you when you do the integral? It gives you 1 over z minus h hat. It gives you the same answer that we saw for z plus, except now the imaginary part of z is negative. It's defined it's the same formula, but it's defined in a different region of the complex plane. Also, something else you can check is that if you then take the limit as epsilon goes to 0 of g minus of z, let me write it as g minus of e minus I epsilon. What do we get? We get a well-defined limit, except in the case where e is one of the discrete energy eigenvalues. Let me come back to that limit in just a moment. However, let me go back up here. Did I write this out anywhere? I don't think I did. Let me write it here. this is a repeat of something that was on a previous page. The limit as epsilon goes to 0 of g hat plus of e plus I epsilon. A moment ago, we just called that g hat of z, but now I'm going to call it g hat plus of z to indicate that it came from taking the limit from the upper side. This is the same formula, I'm just putting a plus on the g's. Likewise, for the g minus, let's define this as definition. Let's define this to be g hat minus of e to the extent that this is defined. And if you go through the same analysis as before, you will find that as I said, the g minus of e, just like g plus, is defined for all values of e except for the discrete eigenvalues of the bound states. All right, now let's see here. So let's compare these limits. We have g plus of e and g minus of e. We have two Green's functions now on the real axis. They're both valid Green's functions. Are they the same? If not, how are they different? Let's analyze that question. So here I've written the formulas for g plus of e written out in terms of energy eigenstates and both for the discrete and the continuous spectrum. If I do the similar formula for g minus, the answer looks the same, except I've just got a minus sign on the right-hand side, like this, n alpha over e plus I epsilon, excuse me, it's e minus I epsilon minus en. I just changed the sign of epsilon, you see, to convert one formula into another. Otherwise, I'm just copying these formulas. Sum on alpha, e prime alpha, e prime alpha, e prime alpha, outer product up above, and then I got e minus I epsilon minus e prime. So if you think about case A, where e is negative, and e is, so let's say case A down here. Case A, e is negative, and e is not equal to any discrete eigenvalue en, then the e minus en is never equal to 0, and just letting epsilon approach 0 is equivalent to just setting epsilon equals to 0. Likewise, in the same thing, in the positive energy term, the e minus e prime is never 0. So what that shows you is that the limit in case A of g plus and g minus is the same. G minus of e is actually equal to g plus of e. If I put it in my diagram here, if we come in case A from the two directions like this, the limit from below as epsilon goes to 0 and the limit from above gives us an operator. I'll put an x here where it's defined, which is actually the same value. Now, if we do it in case B, coming in from above, we got an infinite answer. And the same thing happens if you come in from below, you get an infinite answer. So again, it's not defined at the discrete energy eigenvalues. What happens about case C, where you're here in the continuous spectrum? You come in from above and you come in from below. It turns out in that case, the two limits are not the same. They're not the same for the continuous spectrum. Isn't that strange? Well, let's look at this situation. Let's understand in what sense they're not the same and why they are the same in the gaps between the discrete eigenvalues for negative energy, but they're not the same for positive energy. That means that the G plus and the G minus Green's operators are not the same Green's operators. So they satisfy different boundary conditions. That's what it's going to mean, you see. One, you can imagine, is going to be outgoing boundary conditions, and the other incoming. That's exactly how it is, because of where they came from Fourier transforms of the time-dependent Green's functions. All right, but anyway, let's examine this quantity here. Let's take a look at this. The limit as epsilon goes to 0 of the g hat of e plus I epsilon, call it g plus of e plus I epsilon, minus g hat minus of e minus I epsilon. This is the, you might call this the discontinuity between these two limits coming from the two sides. What is this equal to? Well, this is the same thing as the limit as epsilon goes to 0 of 1 over e plus I epsilon minus the Hamiltonian h minus 1 over e minus I epsilon minus the Hamiltonian h. All right, let's look at this. Now, to analyze this limit, I'm going to not prove anything, but I'm going to proceed by plausibility. Let's take this operator E minus H hat and just replace it by an ordinary number X. Let's do that. And let's consider, as a simpler problem, let's consider the limit as epsilon goes to 0 of 1 over x plus I epsilon minus 1 over x minus I epsilon, which is just what we've got from above if I made this substitution. And now what you can do is you can combine the fractions together, and if you do, what you get is x squared plus epsilon squared in the denominator, and you get minus 2I epsilon in the numerator. So this leads us to an examination of the behavior of this function as epsilon goes to 0. Turns out it approaches a delta function. If I make a plot like this, as a function of x, of the function epsilon divided by x squared plus epsilon squared, like so. Let's think of this function. First of all, just look at this function, just think about it. If x is non-zero, then in the denominator, x squared is non-zero. So as epsilon goes to 0, you can get epsilon over a non-zero denominator. The answer is going to be 0. The limit will be 0. On the other hand, if x is equal to 0, then the denominator is epsilon squared, and epsilon divided by epsilon squared is 1 over epsilon, and that diverges as epsilon goes to 0. So the limit of this function as epsilon goes to 0 is infinity if x is 0, and it's 0 if x is not equal to 0. Reminds you of a delta function, doesn't it? In fact, if we plot this function for value of epsilon, which is not quite 0, small but not 0, what we get is something that looks like this. It's got a width, which is of order epsilon, and it's got a height, which is of order 1 over epsilon, suggesting that it turns into a delta function. In fact, if we integrate over all x, dx of the function epsilon divided by x squared plus epsilon squared, it's an elementary integral, you get the answer pi. And so what this suggests is that the limit, as epsilon doesn't suggest, it actually shows it if you're into this enough, the limit of epsilon divided by epsilon squared plus x squared is equal to pi times the delta function of x. And so to go back to the previous page, that's what this limit is, except multiplied by 2 pi. It's minus 2 pi I times the delta function of x. Hope that you can still see that. And this suggests then that that as far as the limit of these operators is concerned, this limit of these operators should be equal to minus 2 pi I times the delta function of the energy E minus the Hamiltonian H. Now, you may remember when back in the first week of the first semester, when I was talking about functions of an operator, I said you may end up with strange functions like here's reciprocals. They aren't just power series. Here's reciprocals. Here's a delta function. So what do I mean by the operator 2 pi I delta V minus H? This is the discontinuity between the G plus and G minus on the real axis. So let's look at that operator and see what it is. I'll leave off the 2 pi I. We can remember that it needs to be in there. Let's just look at the operator delta V minus H. H hat, what is that equal to? Well, with our assumptions about bound states and so on, we have a sum over the bound states, sum over n and alpha of outer product n alpha times the Dirac delta function of E minus En. You see the Hamiltonian got replaced by its eigenvalues. And then the positive energy contributions integral 0 to infinity dE prime sum over alpha. And then we've got an outer product E prime alpha with itself. And then we've got delta of E minus E prime. All right. So let's look at this in the three cases, A, B, and C. Let's look at this discontinuity, or in this difference between G plus and G minus in these three cases. So case A, I'll remind you, is E negative and E not equal to any En. Now, if that's so, then this delta function on the negative energy terms is 0 because E is not ever equal to any En, and so that's interpreted as 0. That goes away. The delta function in the positive energy term is also 0 because E is negative and E prime, the variable of integration, is positive. And so here you get 0 plus 0. So the answer is that this continuity is equal to 0. Let me just call this, let's call delta as a discontinuity. It's a discontinuity. It's equal to 0 in case A. That's the same conclusion we had earlier, that if you approach from below or you approach from above and the gaps between the eigenvalues, the negative energy eigenvalues, you get the same limit. So the difference is equal to 0. Now in case B, where the energy is equal to some discrete eigenvalue, uh, both these limits coming from below and above are both infinity. And if you subtract them, the infinities don't cancel, they just add. So the answer is infinity. Again, it's not defined for discrete energy eigenvalues. How about case C? Well, in case C, what we need to do is go back to, let's see, where's my formula? I want to look at this formula here. Let's analyze this in case C, where the energy is positive. If the energy is positive, all these delta functions, since ENs are negative, they all just give you 0, so that term goes away. But if E is positive, then it means the variable of integration runs over the value of E, and so it picks up this delta function. And so the answer then for the discontinuity between it's a function of E, the discontinuity operator is equal to, you can do the E prime integral, it's equal to the sum on alpha of the E prime alpha outer product with itself. And in particular, it's not equal to 0. So what that means is that the G minus for positive energies on the continuous spectrum, the G minus Green's operator is not the same as the G plus. In fact, they correspond to distinct boundary conditions in scattering problems, incoming waves and outgoing waves. Now, I've just spent at least one whole lecture explaining these I epsilon denominators. If you take a typical course, not mine, or read a typical book, they'll just say, oh, we need to regularize this integral, so stick in an I epsilon. That's the prescription. So what I've done is I've explained the prescription. I hope you understand why it works. And in cases where if you get confused about why it works, I think the analysis that I've given you, even though it's totally non-rigorous, I think it'll give you the information you need to decide how to resolve the difficulty and understand what really needs to be done. All right, that was my goal in doing it this way. All right. So that is the story of the Green's functions. We have two Green's functions. They're both given by as a function of a complex variable. They're both given by 1 over z minus h, the Hamiltonian like this, when the imaginary part of z is non-zero. But the plus Green's function is defined in the upper half of the complex plane, and the minus Green's function is defined in the lower half. Also, these two Green's operators, Green's functions as Green's operators, these two Green's operators, as I just explained, are equal to one another in the gaps between the discrete energy eigenvalues. So what this suggests is that this Green's operator is a function of a complexified energy in these two different regions are actually analytic continuations of one another. You just continue smoothly and across these gaps and come in. Just go through the gaps between the discrete eigenvalues, and you can continue from the upper to the lower half plane. And with that understanding, then this G of Z then becomes valid everywhere in the complex plane, except possibly on the real axis. So everywhere. So if Z is not on the real axis, or if it's on the real axis but in the gaps between the negative discrete eigenvalues, then this is a well-defined function of Z. And this is called a resolvent operator for complex energies. Now it can be applied for both positive and negative imaginary parts. All right. Now then, how do we interpret the singularities that occur in this G when we approach a discrete energy eigenvalue? Well, the answer is given partly by looking at these expressions here, which are valid when epsilon is non-zero. You can see when epsilon goes to 0, or let me put it this way. If I took this G of Z and I expanded it out, again, in the energy eigenvalues, n alpha like this, what we'd have is Z minus En here, plus the other term for the positive energies. You can see that that this 1 over Z minus En is that as a function of a complex variable Z, this thing is a pole. It has a pole at Z equals Zn. And the residue of the pole is the projection operator onto the energy eigenstate. And so what that leads to is some Cauchy theorem kind of results if you know about contour integration and Cauchy's theorem. Let's draw the complex energy plane again, real imaginary part of energy E. Let's say here's one of the discrete eigenvalues. It means that if I take a contour, which is a circle around one of these discrete eigenvalues, let's call it E sub n, and I do an integral around that contour, 1 over z minus the Hamiltonian. This is the Green's operator, dz. Integrate that. This 1 over z minus h is the Green's operator. It's the resolvent operator. We divide by 1 over 2 pi I because that's what Cauchy tells us to do. That gives us the residue of this pole, which is the projection operator under the corresponding energy eigenstate, like this. All right. Now, as we'll see later on, the knowledge of the Green's operator as we take the limit as z goes to zero, as epsilon goes to 0, either from above or from below, allows us to solve scattering problems. We'll show you that explicitly in a little while. There's something else that happens here too. This discontinuity across the continuous spectrum is interpreted in the language of complex variable theory by saying that the resolvent operator 1 over z minus h. We say it this way. Let me say it all at once. 1 over z minus h, the resolvent operator, is an analytic function of the complex variable z, analytic operator valued function of the complex variable z at all points in the upper half plane and at all points in the lower half plane. And in addition, at all points on the negative real axis between the discrete eigenvalues, it's defined there as well. However, it has poles at those discrete energy eigenvalues. As far as the positive real axis is concerned, the discontinuity across the real axis is interpreted by saying that the continuous spectrum is a branch cut of this operator considered as a function of a complex variable z. Branch cuts, you can move around. They really have arbitrary position. If I move the branch cut around, say here's the positive real energy axis, I might be able to move the branch cut down like this, in effect pushing the continuing the upper solution, analytically continuing the upper solution down across the real axis. If I do, what happens is you may reveal further singularities down here in the lower. This is now what you call a second Riemann sheet. These further singularities down there. These further singularities are the resonances of the system. We've talked about resonances in connection with the excited states of helium. They also occur in scattering problems as well, enhancements in cross sections. And in some sense, they correspond to imaginary energies. So you have poles with real energies. Those are the real discrete bound states, but you've also got poles in the second Riemann sheet, which are connected with the resonances of the problem. So what this is saying is that if you can find the resolvent operator as a function of the complex variable z, and you can do things with it like integrate around loops, or take its limit as we come down to the real axis, or analytically continue it onto a second Riemann sheet, then you obtain the information. You obtain all the information that's needed to define the discrete energy eigenstates and the scattering solutions and the resonances. So this is a way of saying that the resolvent operator, or Green's operator, contains sort of coded within its analytic structure all of the things that you'd like to find out about your quantum mechanical system: the bound states, the scattering states, as well as the resonances. Okay, so this makes people interested in the resolvent operator. Okay, so that's my spiel about the resolvent operator and the energy-dependent Green's functions. Before I go on, are there any questions about that? All right, then the next task before us is to actually work out one of these Green's operators. The only case it's at all easy to do is the free particle, so that's what I'll do. I will outline the derivation of it. So I'm going to use a 0 subscript for a free particle here. So 0 means free particle. And what we're going to want is the G0 we'll do it in 3 dimensions. Let's make it becomes XX prime in energy E, like this. And by its definition, this is the limit as epsilon goes to 0 of the X and X prime matrix elements of what? Of the Green's operator, which is 1 over E plus I epsilon This should be G0 plus. Let's take the G0 plus. This is the outgoing Green's operator. The plus means we come in from the positive side of the complex plane. They take the limit as epsilon goes to 0, minus the unperturbed Hamiltonian, which is p hat squared over 2m, kinetic energy. So this is the matrix element we need to evaluate and take its limit in order to get the Green's operator. I'm just going to outline the basics of this. So the operator in the middle is a function of the momentum operator. And so the way to evaluate this matrix element is to insert a resolution of the identity in momentum space, a d cubed p of outer product pp with itself, like so. And if we do, we get a p scalar product x prime, which of course is a plane wave. Likewise, now this operator in the middle has got p hat is the operator acting on an eigenstate of itself p, the p over here, this eigenstate of momentum. And so that p hat can be replaced by the eigenvalue. And if we do, that number, that becomes a C number and can be taken out of the matrix element. That then leaves the X here adjacent to the P, which is another plane wave. And so if I put those pieces together, those thoughts together and clean it up a little bit, I get the limit as epsilon goes to 0, integrate over three-dimensional momentum over 2 pi h bar cubed. These denominators came from the normalization of the plane wave states. Then we have e to the I, p dotted into x minus x prime, like so, divided by e plus I epsilon minus p squared over 2m, which is now a C number, not an operator anymore. So then evaluating the Green's operator for the free particle, Green's function for the free particle involves just doing this integral. One of the things you can see right away is the integral depends only on the difference between x and x prime. So this is a function of the difference, the vector difference x minus x prime, because that's what appears here. The reason it turns out that way is because the Hamiltonian that we started with, this h hat, is translationally invariant. And that gives rise to this fact here that it's a function of x minus x prime. This Hamiltonian, by the way, is also rotationally invariant. And one can show that this not only depends on the vector x minus x prime, it actually only depends on the magnitude of that vector. Allow me to make this definition. Let's let capital R be x minus x prime. And then let's let just R without any arrow on it be the magnitude of capital R. Let's make those abbreviations. So this thing actually turns out to be a function of just capital R alone, not just the vector. So this integral can be done by contour integration. You can do the angular part analytically, and then there's a contour integration for the radial part. And all the details are contained in the notes, and I'm not going to take class time to go over those integrals. But I'll just quote for you what the answer is. The answer turns out to be the following. Is a G0 plus of x prime in energy E. I'll remind you that the plus means that it's the outgoing Green's function, and the 0 means free particle. This is a common factor out front is minus 1 over 4 pi, 2m over h bar squared. And then we get cases here, depending on whether the energy is positive or negative. By the way, for the free particle, the spectrum for the free particle is, of course, just trivial. We just have a continuous spectrum for positive energy, and there are no bound states for negative energy. So there's no issue of discrete bound states. But in any case, what we find when we do the algebra is we get this prefactor times e to the I kr over r. And this is in the case where the energy is positive. And if the energy is negative, I get e to the minus kappa r over r.
Excuse me, could you shift the notebook down a little bit?
Yeah, thank you for telling me that.
Thank you.
Okay, this is what we get. We get e to the ikr over r for positive energy, and e to the minus kappa r over r for negative energy. And this is for the outgoing Green's, the energy-dependent Green's function. I already defined the r for you here, but let me define the k and the kappa. For positive energy, the k is defined by writing E is equal to h bar squared k squared over 2m. It's the equivalent wave number k. When the energy is negative, we take the absolute value of energy, which is positive, and write it as h bar squared kappa squared over 2m. So kappa is like the analog of k, but for negative energies. For negative energies, you know, the solutions are always damped or growing one or the other. All right. So if we take this Green's function and we multiply it by a time-dependent factor, e to the minus IET over h bar, which is what you'd get by this finger poking in the lake, kind of a picture, then this G0 plus represent waves which are radiating outward from r equals 0. And you can see at r equals 0 it diverges, so there's a singularity there. The wave field, the Green's function, is singular exactly at the source of the driving term. It falls off as 1 over r and it represents outgoing waves. If you do the same thing for the incoming Green's function, then we can express it too with a formula plus and minus. And what happens is the phase factor in the positive energy solution gets a plus or a minus sign on it. What that means is the G0 minus is a wave field which is radiating inwards and reaching a delta function at capital R equals 0, right on top of the driving term. On the other hand, for negative energies, the plus and minus Green's functions give you the same value. And they have to, because remember, I said if you approach from above or below on the negative energy axis and you're not on top of a discrete energy eigenvalue, then the limits from the two sides are the same. And that's what comes out by a rather detailed but explicit calculation of this energy-dependent Green's function for the free particle. So it conforms with the expectations that we had based on the general theory of Green's functions and operators. Okay, I think that's all I want to say about energy-dependent Green's functions. There's a whole world out there of this stuff. If you do any more advanced work in quantum theory, you'll definitely use Green's functions. Any questions about this so far? All right, then let me proceed. So now the question is, what's it good for? It's a long build-up. Let's show you now how we use it. We want to use it to solve a scattering problem. We have a Hamiltonian, which is going to be H0 plus a potential V of X, let's say. V of X does not have to be rotationally invariant, but we will assume it dies off rapidly enough. And H0 is the same thing as the kinetic energy, so it's P squared over 2m. And I'll omit the hats here, but these are really operators. Let me rearrange the Schrodinger equation in the following way and write it as E minus H0 acting on psi of X is equal to the potential V of X times psi of X. So that's just the Schrodinger equation. However, we're going to interpret it in a novel way by saying that we're going to treat the right-hand side as if it's a source term. That is, we'll just define this to be S of X as a source term. And what that means is that we can write down the general solution of this equation then as psi of X is equal to, well, we need the Green's operator for the operator E minus H0 for the unperturbed Hamiltonian. So this is going to be that's this G0 that we worked out up above. So the exact solution then is equal to a solution of the homogeneous equation, which I'll denote by phi of X like this, plus an integral over source d cubed x prime of some Green's function for the free particle. I'll put a G0 there to indicate free particle as a function of x prime and energy E times the source evaluated at x prime, but that's the potential V of x prime times the wave function psi of x prime, like so. Okay? And this is a homogeneous solution. It means E minus H0 and phi equals 0. So phi is a free particle solution, you see. I'll use psi here for the exact solution of the full Hamiltonian. I'll use phi for a solution of the free particle Hamiltonian. Okay, so for any choice of the free particle solution, and for any choice of a Green's function for the free particle, this gives us an equation for psi for a solution of the Schrodinger equation. However, this equation that I've written down is not a solution for psi because the psi appears on the right-hand side as well as on the left-hand side. That's because the driving term depended on psi. So it's not an explicit solution. Rather, what it is it's an integral equation which is satisfied by this solution, which in some sense is equivalent to the original Schrodinger equation, but which is better for applications to scattering theory, mainly because it incorporates boundary conditions, as we will see. So in any case, remember, this is not a solution, it's rather an equation satisfied by the solution psi of the Schrodinger equation. Now, we're going to be interested in problems in which we have an incident plane wave. That's part of our boundary conditions. So I'm going to assume that this free particle solution phi here, phi of x, is a plane wave solution. I'll write it as e to the I k dot x divided by a normalization, I'll take to be 2 pi to the 3 halves. And I'll write this also in Ket language as the scalar product of x with k vector, like so. And the reason for the 3 halves, pi 3 halves normalization is to make the scalar product of two of these wave functions, k with k prime, to be equal to a Dirac delta function of x minus k minus k prime. Three-dimensional Dirac delta function. By the way, in this approach to scattering theory that I'm beginning now, using Green's functions, we will not be using boxes. The boxes are gone. This is a definite advantage over this approach to scattering theory with Green's functions. We had to use boxes for time-dependent perturbation theory. All right, now, so that takes care of the homogeneous solution. It's a free particle solution. I'll write it as phi with a k subscript, in fact, to indicate the k value of the incident plane wave, like that. Let's do that. Let me clean up my desk here a little bit. Get this over here a little better. Okay. Now, what about the Green's function? What Green's function should we choose? Well, for a real scattering problem, we want waves that are radiating outwards. And so we want to use the outgoing Green's function here, and G0 plus. So for the desired scattering, the desired boundary conditions on the real scattering problems we want to solve, this is the correct Green's function to use. It's for a free particle Green's function, outgoing, G0 plus of XX prime and energy E. All right. Now then, so then this then gives us an integral equation for the wave field psi, where now the phi is a specific homogeneous solution given plane wave, and and we're using the outgoing Green's function. Now, the question is whether or not the solution to this equation is unique. And I can give you a plausibility argument that it is unique, and it runs something like this. If we think about the classical analog of this scattering problem, then the incident plane wave becomes a beam of particles, which all have the same momentum being directed at a target. Real beams have to be turned on at some time. But if we imagine the beam's been on for a long time, then what happens is you get set up, and what becomes set up is a steady state in which there's a steady flux of particles. If at any point in space there's a steady flux of scattered particles leaving the scatterer, there's also a steady flux of incident particles as well. Typically, both of them are there. But in any case, it's independent of time. Now, to make it independent of time, you had to turn on the beam and then wait long enough. You had to wait long enough for the beam to reach the target and then to start scattering from it. And when it does that, then there becomes a front of scattered particles that move outwards. But behind the front is established a steady state. So if you're at any location in space and you wait long enough, the steady state will eventually take place where you are. The further you are away from the scatterer, the longer you have to wait. But like I say, let's imagine we've waited a very long time, so essentially all of space is filled up with a steady state. So what this classical situation shows you is that the wave vector of the incident wave, the k here, determines a unique steady state in the classical problem. It does that. And so it's plausible that similar in the quantum mechanics as well, is that the incident, a specific k vector in the incident plane wave means that there's a unique psi that satisfies this equation. And this, in fact, is true and can be proven by using the theory of integral equations, Fredholm integral equations, of which this is an example. There's a mathematical theory that shows that the solutions are unique. And so because of that, if we accept that now, let's accept that. Then the psi here is also parameterized by k. So let me modify this equation just by putting a k subscript on the side to show that it's dependent on once the k value is given for the incident wave, then the psi is uniquely determined. Okay. Now, okay. So you may notice, by the way, that this limiting process of putting in epsilons and letting them go to zero and all that kind of stuff that went into the construction of this G0 is actually sort of related to this fact that in the classical picture you need to wait a long time. You essentially need to wait an infinite amount of time to set up the steady state, because you need to wait for transients to go away, and that's in effect what's happening here. That's the meaning of the use of that Green's function that's gotten those transients have been dispensed with. All right. So this equation, which I've now created up here, boxed in this manner, is called the Lippmann-Schwinger equation. Lippmann-Schwinger. And I could tell you a joke about Lippmann. His name was Bernie Lippmann. A friend of mine used to ride with him on a carpool over to Livermore every day. Anyway, Schwinger, of course, is the famous Schwinger Nobel Prize winner for the credit for the discovery of quantum electrodynamics. Anyway, this is called the Lippmann-Schwinger equation. We can put the Lippmann-Schwinger equation into Ket language, which makes it somewhat easier to write. And if we do that, what we get is this. We get psi k like this. I'll write Ket psi k for this wave function here. And for the free particle wave function, I'll just write it as k without the phi on it. And then for the integral here, this is the multiplication of the operator, the Green's operator, times the potential times the wave function. So I can write it this way as G0 plus with a hat on it of energy E times V, which is of course a function of X, that's the potential, times psi k, like so. And so this is a Ket language for the Lippmann-Schwinger equation. And in this form, it's no longer necessarily, a single scattering in 3D. This could be a multi-particle problem. It could be a set spin. It could be relativistic. It could be a field theoretic problem. They all work. This Ket language incorporates all of them. All right. Now here's an issue here. The Green's operator has an energy parameter E, and the incident wave has got a wave vector K. How are those two related? And the answer is they're related by the free particle relation. So the E here is equal to, it's the usual thing, E is equal to h bar squared k squared over 2m. Now, why is that? Because this particle isn't free. There's a potential there. The reason is this, is that the phi k so here's the mathematical reason. The phi k is a homogeneous solution. So it's a solution of E minus H0 acting on phi k equals 0. So phi k is a free particle solution of energy E. And that just tells you that this energy E has to be related by that relation. Here's another way of looking at it, however, is that when you think about launching particles at the scatterer V, we assume that V dies off so that at great distances it can be ignored. And at large distances then, where we launch the particles, both the exact solution and the incident wave are free particle solutions. And the energy has to be equal to E because the potential isn't, it has to be equal to E because they have to be free particle eigenfunctions in that region because the potential is negligible. And it just goes away in the Schrodinger equation out there in those regions. Now, on the other hand, the energy E, the eigenvalue of an eigenfunction, is independent of X. It applies everywhere. So the same E applies everywhere in space. That's to say, psi k of X is an eigenfunction of energy E everywhere in space. Whereas phi k is an eigenfunction of H0 everywhere in space. All right, anyway, that's this, and that's the relation between the E and the K. And this is the form of the Lippmann-Schwinger equation in Ket language. All right, now, any questions about that before I go on? The Lippmann-Schwinger equation is absolutely fundamental for scattering theory. Any further questions before I go on? Okay, now the question is, how do we solve this? What can we do with this? Actually, I'm going to address another issue first. Let's ask, what would have happened if we'd used the incoming Green's operator here, Green's function, instead of the outgoing one? What would have happened? Well, if I'd done that, let me go back to let me go back to it in equation, in wave function form. It's in this box here. If I'd used a G0 minus there instead of a G0 plus, maybe before I address that, before I address the G0 minus, let me elaborate a little bit on the G0 plus. Let's look at what this equation means. We decided in scattering theory that the exact solution was going to be equal to the incident wave plus the scattered solution. That was the scattering part, scattered wave. Scattered wave is defined as the difference between the exact solution minus the incident wave. Therefore, this term is the scattered wave, okay? And so it ought to have the outgoing boundary conditions. It does because of G0, in fact. But we talked about that before, as the scattered wave is supposed to be outgoing asymptotically. Now, on the other hand, this is expressing the scattered wave at all values of the variable x, the field variables x, not only ones far away, but also close in, and explicitly in terms of an integral over the Green's function, the potential, and the exact solution psi. All right, so what does this mean? Well, let's suppose we take our scatterer here. Let me draw the blob here as v of x. So this is the region where v of x is non-zero. They're integrating our x prime here. X prime is a variable of integration, which therefore runs over the range of the potential. So this integral is actually localized. It's localized to the range of the potential, v of x prime. So and then the scattered wave itself is a sum of Green's function waves centered at point x prime, weighted by the product v times psi k at x prime. So at a given x prime value here, what you've got is spherical waves that are radiating outwards like this, you see, coming outwards from this. At a different point, you've got different spherical waves radiating outwards. And so the total scattered wave is the sum of all these little spherical waves radiating outwards, which they interfere with each other and combine together to give you the overall scattered wave going out in different directions. Now, this is just like the problem of scattering of electromagnetic waves by a conductor, like in radar. Is the currents in the metal radiate the scattered wave. And that's what's happening here. Is the scattered wave is in effect radiating. Little g0 is the element of it's the delta function of the radiated wave is the idea. By the way, if all of these scatterers were in phase with each other inside this potential, we start to see some things qualitatively about the nature of the scattered wave. If they were all in phase with each other, then they would constructively interfere in going out in different directions. And what that means is the scattered wave, the assembled scattered wave moving away from the scatterer would be isotropic. This, as we saw earlier, is what we called S-wave scattering. It's isotropic. On the other hand, if different parts of the scatterer were out of phase with one another, then you get a directionality to the scattered wave. So any directionality is due to the fact that these little scatterers these little radiators are out of phase. Well, the phase of the radiators depends on the potential V, which is presumably slowly varying over the range of the potential, times the wave function psi, which is a oscillatory, like that. So if the wave function psi in the region x prime has a long wavelength, long compared to the dimensions of the scatterer, then you see these scattered waves, in fact, are in phase with one another, and we do get S-wave scattering. That leads us back to our earlier conclusion that S-wave scattering occurs when the wavelength of the incident wave is large in comparison to the size of the scatterer. So that comes out also, but it gives us a picture of these waves. Now, if we had used G minus, G0 minus instead of G0 plus, the picture would be quite different, because instead of these little point sources here being waves radiated outwards, they'd be absorbing waves coming in like that. They'd all be coming in. Can you see my little diagram? Bring it up here. So the general picture then would be, we'd have an exact solution, which would be a sum of an incident wave, which is just the same as before. It's this wave coming in like this. That hasn't changed. But instead of the scattered wave, what we'd have is waves propagating inwards from infinity and combining together with the incident wave in order to create a solution of the Schrodinger equation. So if that's what we get if we use the G0 minus in here instead of G0 plus, we'd get in other words, we get a solution which is totally non-physical. We get the incoming solution. It is, however, a solution. And the question is it good for anything? The answer is yes. It turns out these incoming solutions are actually important in various theoretical developments, even though they're impossible to establish experimentally. And the outgoing solutions are the ones we want for talking about ordinary scattering processes. We'll see this later on, how the incoming solutions play a role. All right, all right. So I hope that gives you a picture then, something of a picture of the um, of the scattering process here. By the way, regarding the question of the phase dependence of the individual radiators, you see this turns into an antenna problem. Is the idea. That's what you've done with these sources. You made it into an antenna problem. A scattered wave is what's radiated by these little antennas. Since Russia is on our minds, back in the 1970s, it was part of the arms control treaties with Russia was an abolition on what they called phased array radars. A phased array radar is an array of radars in which you electronically control. Each one sends out a radar signal, radio pulse, but the different pulses can be across the range of radars can be phased differently. You can give phase increment, for example. And if you do, they interfere with each other in such a way as to change the direction of motion. If you have the phase increasing to the right, then the waves will bend like this. If you have the phase increasing to the left, then the waves interfere with each other in order to make the outgoing wave vector and the other off to the left. And so what this allows you to do is by changing the phasing of the different transmitters, you can sweep the sky at electronic frequencies, very rapidly, microseconds, across the sky by changing the sweep of the arrays. So this was considered destabilizing, and there were arms control treaties to control these phased array radars. All right. Anyway, all right. Anyway. Okay, so that's the incoming solutions. Now then, what is this good for then? Let's go back to the Lippmann-Schwinger equation for the outgoing solutions. I've represented in Ket language up here. Let me rearrange this equation and bring the phi terms to one side and the k term to the other side. If I do, we get this. We get the plane wave, the incident wave k is equal to the following. It's equal to 1 minus G0 of E. The greens, I'll leave the hats off, but this is the operator here, G0 plus of E, times the potential V, and that all multiplies onto psi sub k. And so what we see is we have an operator here in the square brackets, which maps the exact solution into the incident plane wave. This would mean that if we could invert this operator, we'd have an operator that would map the incident plane wave into the exact solution. Let's give this a name. I'm going to call it omega plus of energy E is equal to 1 minus G0 plus of energy E times potential V inverse. Let's make this definition. And this is called the Muller wave operator. That's the Scandinavian O, not a Greek phi as a slash through it. The Muller wave operator. I have no idea if that's how to pronounce the name, but that's what it is. Muller wave operator. It's parameterized by E. By the way, we can generalize this and make omega a function of a complexified energy Z like this is 1 minus G of Z. We don't need G0 of Z. It's a free particle G0 potential V inverse, like so, in which case omega plus of E is the limit as epsilon goes to 0 of omega of E plus I epsilon. Anyway, this is kind of an aside here in terms of dealing with the Muller wave operator. But anyway, let's go back to this definition here. So what we see then is that if I can evaluate this inverse to get this Muller wave operator, I've got something that maps the k into the psi. So let me just write it out this way then, is that psi sub k is equal to 1 minus G0 plus, I'll put it in terms of Muller wave operator, it's omega plus of energy E acting on phi, acting on k, plane wave k. In fact, since I messed it up, let me write it again on a clean page here. The exact scattering solution is equal to omega plus of energy E acting on k, the incident plane wave. Okay. All right. Now, how does this help us? Well, it can help us with perturbation theory. Omega plus of E, as I just explained, is the inverse. I'll write it this way: is 1 over 1 minus G0 plus of energy E times potential V. And we can expand this out in a formal Taylor series, treating operators as if they were C numbers. We get 1 plus G0 plus of energy E, potential V, plus G0 plus of energy E, potential V, G0 plus of energy E, potential V. That's the operator squared plus dot, dot, dot. You get an infinite series like this. And if we take this infinite series and we plug it in here into the wave field, what we get is we get psi k, the exact scattering solution, is equal to, the initial term is just 1, so we get the incident wave k. The next term is plus G0 plus of energy E times V times k. The next term is plus G0 plus of energy E times V times G0 plus of energy E times V times k, and so on like this, plus dot, dot, dot. And this is the Born series. This is called the Born series for the scattering solution. It's basically just inverting this omega operator and writing and expanding things. And the V is the potential here, you see. So what you're really doing is expanding, really expanding in powers of the potential. Here's this linear, it's quadratic, and so on. That's the Born series. Now, before I proceed with the Born series, I have to go back and cover a topic which I forgot to do earlier, an important one, as a matter of fact. So let's put this Born series on hold and allow me to go back to the Lippmann-Schwinger equation in wave function language. It is that psi of x is equal to phi of x, which is the free particle solution. And if I put in the explicit form for the Green's function, it's minus 1 over 4 pi times 2m over h bar squared times the integral b cubed x prime, like this. And if I write in the Green's function explicitly, it is e to the ik, the absolute value of x minus x prime, divided by x minus x prime, times the potential evaluated at x prime, times psi evaluated at x prime. Okay? This is the Lippmann-Schwinger equation with the integral, the Green's function written out explicitly in wave, all in wave function language. Now, as I explained, the second large term here is a scattered wave. Therefore, it must have an asymptotic form that goes like e to the ikr over r times f of theta and phi, because we argued for that previously, that was the asymptotic form of the scattered wave, where f is a scattering amplitude. So let's take the limit of this. Now, this version of the scattered wave, which I've written down here, is valid for all values of x, not only ones that are far away out in the asymptotic region, but ones that are close in, down where the potential is active. But in order to get the asymptotic form in the scattering amplitude, we're going to need to let x get large and move far away from the scatterer. So let me draw a picture here. Let's have axes x, y, and z. Let's have our potential here, which is, as I keep saying, is allowed to be lumpy. No, I want to make a bigger picture. Let's make a bigger picture here, like this. X, Y, and Z. Here's our potential, which is allowed to be lumpy, like this. There's a plane wave coming in here, like so, the k vector. And let's choose what I'll call an observation point out here. Let's call it x vector like this. And that's equal to radius r times r hat. So let me define r as the magnitude of x, like so. And r hat is equal to x vector divided by r. All right? Let me draw the radius vector out there like this. And we'll think of this as being an observation point. Now, let's assume, for simplicity, let's assume that the potential V of x is strictly equal to 0 when the magnitude of x is greater than some cutoff. Let's call it r naught, like so. So there's some sphere we can draw here, and inside the potential is rigorously 0. Real potentials die off gradually, so that's an issue to deal with. But for simplicity, let's assume this. And let's assume that our observation point is far outside this cutoff radius, so it's way outside the place where the potential cuts off. Well, in this scattering wave, let me write down the scattered wave again. It's minus 1 over 4 pi 2m over h bar squared integral d cubed x prime. Green's function is e to the I k, absolute value of x minus x prime, divided by x minus x prime, potential v of x prime, and then psi of x prime, the exact solution. Okay, this was the scattered wave. So this scattered wave involves an integral over x prime. If I take a typical point here, let's call it right there, then the variable x prime is a variable of integration and runs over it's limited. You see, the integrand is multiplied by the potential v, so the range of x prime is also limited by where v is non-zero. So what that means is that x prime is a small vector compared to x, the field point. The distance between x and x prime involves this triangle that we have here. So let's see. So what that means is that r is much greater than r prime, which is to say the absolute value of x is much greater than the absolute value of x prime. X prime is a variable of integration, but this is true over the entire range of integration. So that means that r prime over r, or x prime over r, is small quantity. And so let's expand this integrand out in powers of x prime over r. Let's start with the absolute value of x minus x prime. If we do this expansion, if x prime is equal to 0, what we just get is r itself. The first correction term turns out to be r hat dotted into x prime, like so, which can also be written as r vector minus x vector dotted into x prime vector divided by r, like so. This is actually part of a power series expansion in inverse powers of r. You can see this is order r. The next term is of order 1 because this is r hat here. And the next term after that would be order 1 over r. So the terms that are order 1 over r are going to go to 0 as r goes to infinity. So this expansion that I've done for the phase factor here, we need to carry it out through the order 1 term, because to get the phases right, you need to get it within a factor of 2 pi. So we need the first 2 terms in order to get the asymptotic form of the phase correctly, and that's why I carried this out to the first 2 terms here. But I'll neglect the term that goes as order 1 over r. As far as the denominator goes, however, we can just stop with the first term r here, because the next term is a higher order correction. So if I make that expansion, then in the Green's function, then the phase factor then e to the I, c to the plus I k absolute value x minus x prime divided by the absolute value of x minus x prime goes over into e to the ikr over r. The ikr comes from the first term here, times e to the minus ik. Let me write it this way, as r hat dotted into x prime. Okay? Now, to go back to this picture, the r hat is the direction to the observer. If we think of x as the position of this, here's the r hat vector here. Allow me to make the following definition. Let's take k times r hat, which is the quantity that occurs in our expansion of the Green's function, k times r hat. And let's define this to be k prime. The idea is that the K prime is a wave vector which points to the observer is distinct from the K, which is the wave vector of the incident plane wave. But it has the same magnitude as K as you see if you square both sides. So in other words, it has this K prime corresponds to the same energy as this vector K does. And so if I do that, then this expression becomes e to the I k r over r times e to the minus I k prime dotted into x prime, like so. And if you now look at this, so now you've got the e to the I k r over r. This is the factor that we expect for the asymptotic form of the wave field. This is going to be underneath this integral sign here for the scattered wave, but this factor is independent of the variable of integration and can be taken out. And so the scattered wave then looks like this. It looks like e to the I k r over r times the rest of it I'll call f, where f is equal to the rest of this integral, which I'll write out for you, becomes minus 1 over 4 pi 2m over h bar squared. Then we have the integral d cubed x prime. Then we have this part of this what's left of the Green's function, e to the minus I k prime dotted into x prime. Then we have the potential v evaluated at x prime, and then we've got the wave function psi sub k evaluated at x prime. All right. And now, so this comes from looking at the asymptotic form of the scattered wave in the Lippmann-Schwinger equation. Now, this integral, which appears here, this e to the I kx can be, except for normalization, it can be regarded as a plane wave. In fact, it's a wave which in Ket language would be denoted k prime in the notation we are using for free particle waves, except it's complex conjugated to make a bra here, you see. So this thing is proportional to a matrix element of the potential V between, on one side, a free particle solution with the outgoing wave vector, and on the other side, the exact solution. If you put in the normalization factors, this becomes 2 pi the 3 halves times the scalar product of k prime with V in the middle and psi sub k on the right-hand side. So we get an interesting formula that the scattering amplitude f of k comma, let me write f of k comma k prime is equal to minus 1 over 4 pi 2m over h bar squared 2 pi to the 3 halves, a bunch of 2 pi factors, and the main thing is the matrix element k prime v psi of k scalar product. Let me box that. In other words, we obtain an explicit formula, or it's an exact formula for the scattering amplitude in terms of this scalar product, which appears here. And it's actually quite an interesting result because the f, by the way, previously I was calling f of theta and phi. You know, this was assuming that this just indicating the dependence on angles of the outgoing direction. The k prime direction here really was the old theta and phi. But I'm changed notation here and write it as f of k comma k prime because I don't want to assume that k is in the z direction. This now allows it to be k and k prime to be in arbitrary directions. In any case, the main point here is that this is expressed by some constants times this matrix element. And what's interesting about this matrix element is that since V is localized into it's localized, it's a small region, you know, at the scatterer, it is the scatterer. The integral which goes into calculating this matrix element is of a limited range of integration. In other words, it comes from low distance radii. Whereas the F is a property of the asymptotic wave field at large distances. So this formula connects things happening at small distances to things that happen at large distances. This is also exact, by the way. This is, however, not by itself a useful formula for calculating the scattering amplitude because we'd have to know what the exact wave function was in the presence of the scatterer in order to be able to use this formula. But as we'll see, this formula is useful for approximations. In fact, if you now allow me to go back to the Born approximation, which I put on hold a minute ago, you'll find it here if I can find it. Born approximation involved expanding the Born series. Let me call it the Born series rather than the Born approximation. Here it was. This is written in Ket language. It's psi k is, see, these are just the power series of expanding this Muller wave operator. And it's an operator acting on the incident plane wave k like that. So if I take this psi sub k, I hope you can see it here, this psi sub k here in this formula, and put it in over there. In effect, what I want to do is to take k prime as a bra potential v, and I want to multiply this whole equation from the left by that, and then multiply by these constants here, and then I'll get f. So if I do this, here's what we get. We get f of k comma k prime. Constants are the same, which I've copied, minus 1 over 4 pi 2m over h bar squared, 2 pi to the 3 halves. And then the matrix element now looks like this. It becomes k prime v k plus k prime v g0 plus of energy E times V times K plus K prime V G0 plus of energy E times V times G0 plus of energy E times V times K plus dot 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 like so. And what we have here is the Born series for the scattering amplitude. Explicit formulas for the scattering amplitude at all orders of perturbation theory, where the potential V is taken as the powers of the perturbation. Here's first order, second order, third order. This first would be called the first Born approximation. That's the second, that's the third, and so on. All right. Well, I see I'm out of time. The first Born approximation, which is the first term, I think you see if you square it, what you're going to get is the Fourier transform of the potential evaluated at the momentum transfer. This is just what we got from time-dependent perturbation theory. So that's the first thing I'll take up on the lecture on Thursday, is connecting it with what we did earlier with time-dependent perturbation theory. But now we have all the higher order terms as well of the scattering series, and quite a few other things that can be developed using those Muller operators and Green's functions and incoming and outgoing solutions, which I'll tell you about that in the next lecture. So are there any questions about this? This is some pretty amazing stuff. It's amazing that you can do this kind of stuff with scattering theory. To my mind, it's just a whole sequence of miracles. And the most fundamental miracle is that anybody ever figured this out in the first place. But we're not yet done with the amazing things that come out of this. All right, if there's no questions, then I'll stop screen share. And I will pause the recording. Stop the recording.